Okay, let's get started. So welcome everyone to another lecture in our ID 5130 parallel scientific computing course. So in the last lecture we looked at some of the basic functions, or essentially about the collective communication functions. Such as we looked at something known as the broadcast, and we looked at gather, then a scatter function and things like that, right? Okay, so today I would like to essentially first showcase some of the sample programs, mostly written in C, and then one of them kind of written in Fortran. Showcase some of the sample programs which utilize some of these collective communication. So we will kind of run them, and after that, depending on the time, we would look at one final function that is basically all gather. We would kind of present the motivation and then see how this function works, and then we will move on to, depending on the time, to something that is kind of very important, that is the MPI derived data types. Okay, all right, so then first let us switch to some of the sample programs. So let me kind of rearrange it here. Okay, so the first sample program I would like to showcase is the MPI broadcast. So let us say Emacs program broadcast.c. Okay, all right, so here is the broadcast program, a simple broadcast program in MPI. Okay, all right, so what it does is basically you have stdio, stdlib, and mpi.h included, and you have main with command line arguments written here. Then you have essentially my ID, that is to store the rank of each of the processes, and then size tells you the number of processes, and then we have a tag that is actually not required because we would not be using point-to-point communication. Okay, and then you have int buffer. So this buffer is something that we would like to send or broadcast, and that broadcast is basically buffer is initialized to 0 on all the processes. Okay, and then you have MPI status. So this is basically a data type of type MPI status. Okay, now this can even be MPI status ignore if you do not want to use it. Okay, so that's fine. Then we are initializing MPI by a call to MPI initialize. Then we have our standard function calls, that is MPI communicator size, which will give us the number of processes in the communicator, and then this will basically fill the my ID of my rank, or fill the rank of the of each of the processes, right? Okay, so every process will get its own ID, and then depending on the ID, so what I'm saying is here, because we would like to broadcast, that means the same information of the same size will be sent to all the processes. So we have buffer, which is a single integer, and then if you happen to be on process 0, okay, then we are filling the buffer to be 327, okay, some number here. Then what we're doing is essentially we are calling this function. This is basically a collective communication function, and that is called on all processes. Like, depending on what we learned yesterday, we have to call it on every process. So MPI broadcast will be called by all the processes, and then we are sending the address, that is ampersand buffer, and this is basically one variable, that is one value of the buffer is what we have to send, and we were sending an integer, MPI integer, and then we are sending this 0 is basically for the broadcast. This is basically sent from 0, right? So 0th process is sending it, and then MPI communicate world tells you that this is the default communicator for MPI. And then if my ID equal to 0, then it is printing broadcasted values on process R, and then this one is the second printf statement here would kind of print what is the my ID and then what is the buffer. Okay, so whatever is received by each of the process. So this will be printed by all the processes, including process 0, right? because that value will be because it will be broadcasted. Okay, then we have MPI finalize. So this is the final MPI call in any MPI program. Alright, so that seems fine. Let me go and compile this using my OpenMPI compiler. So I would compile it with MPI CC program broadcast.c. So just compile it like this. Okay, it compiles, and this MPI run minus np4./a.out. Okay, so essentially broadcasted values on process 0. This line is printed by process 0, and then including process 0, all other processes have received 327. Okay, 0, 1, 3, 2, they have all received 327, and as you can see, because they are competing for this standard output resource, right, there is the output, the order of the output is kind of unpredictable, because it kind of depends on how they get the handle of the standard output. I just run it again. You can see that it prints 2013. Okay, fine. So that is about the broadcast program. So the second program we would like to look at is the program, let's say scatter. Okay, because this is not exactly the same as broadcast, because in scatter you're working with a big array, and then different values of this array would be broadcasted to different process, right? In a scatter, that is how the scatter is different from the broadcast, right? In broadcast, the same value will be sent to all the process. In scatter, chunks of the array that we have will be sent to a different process. Okay, so in the scatter program here, what I have is we have again, of course, the initialized, the include of the header files. Then we have the main program. Then again, I probably would not need this tag here. I think it's coming from previous point-to-point communication, so I don't need it. Then we defined my ID to store the rank, and size to store the number of process. Then what we have is we have a send buffer, which is a pointer, and then we have a receive buffer, and both are of integer. Okay, send buffer is a pointer to an integer, and receive buffer is a integer itself. And then we have the MPI status. Then of course the first three function calls are MPI initialize, MPI communicate, communicator size, and MPI communicator rank, which will initialize and fill the number of process and the ID on each process. Okay, then what we're doing is that we are sending, or we are allocating memory for send buffer, right, only on the root, or we are only doing it on the host process, which we designate as process 0. Okay, because as you recall, scatter will only send chunks of this thing, so we don't need the send buffer to be allocated on all the process. So my ID equal to 0. If you happen to be the process 0, then you allocate send buffer to be of size, depending on the number of process you have, and then we are basically allocating a send buffer to be of the size of number of process. Okay, that means if you have, so this is basically an array of length, size, right, or n procs, right? So we have that, and then we can send one integer each to each process from process 0. Okay, and then once you allocate the memory, you can also fill the memory with some value. So I just use some 100 plus I times 5 plus I, something like this, some values to temporarily as placeholder for the send buffer values. Then what we are basically doing is that we don't need to allocate receive buffer, because receive buffer is just a single integer which is already allocated here, so we don't need dynamic memory allocation here. Okay, we need dynamic memory allocation for the send buffer, because the size of the communicator would only be determined by here. That's why I have used the call to malloc here. Okay, again MPI scatter. So this is basically a collective communication. So all processes will call this function, right? Okay, and then we have MPI scatter, and then send buffer will be sent, and then the send count is 1, send data type is MPI int, and then receive buffer is the address. So we are saying ampersand receive buffer, and then we are receiving one count of MPI integer type, and then everything is basically scattered from process 0, and then we have MPI communicate world as our communicator for this particular process. And then once the data is being sent, then if my ID is equal to 0, then this should have been the sent values, right, or the received values on process R. This is fine. Now what we have here is that all we have basically a printf statement. This is basically printed by all the process, right? All the processes will print this message. Then if my ID happens to be 0, I am freeing the send buffer, okay, and it need not be done on other processes. And then finally we call MPI finalize, okay. So that is the program. Let us see if it compiles and runs. So this is MPI cc program scatter.c and then MPI run minus mp4./a.out. Okay, I'm just running with 4 processes. Okay, so the received values on process are on process 3 it has received 118, on process 1 106, and process 2 1112, process 0 100, right? 0, so 100, 106, 112 and 118. Of course the order is unpredictable because every process tries to it will get an access to standard output in, and there is a race condition that is happening. Okay, now of course that is the values that we have printed here, so it seems to be working fine. Let me run it with maybe 3 process and see if it runs or if there is an error. Okay, it seems fine. So it's 0 works on 100, 106 is on process 1 and 112 on process 2. Okay, this seems to be working fine. Okay, so then my program scatter is also working fine. Then let us look at the next program. The other program I would like to showcase is the program gather. Okay, so program gather happens to be, or the gather function does the exact opposite of what the scatter function does. So in a scatter you have an array and then you are sending parts of this, chunks of these arrays to different processes, whereas in a gather function you basically have you're gathering some data from everywhere, from all the processes onto one particular process, right? Essentially you're getting a chunk of memory or a single integer or a chunk of integers or floats or something from every process, and then all that is received on a particular process on process 0. So this is something, the gather is something what we would use in the context of a global sum, right? So we said we can use the gather to calculate, to kind of I mean not exactly in a global sum, rather than if you want to have parts of these arrays to be collected on as a big array on one particular process. Okay, then so we basically let us look at the code. So we have the basic header files included and then the main program. Again, I don't need this, so I'll be doing this for all the programs because I have copy pasted some of these things from the collective function calls. Copy pasting is not always nice because it introduces new bugs in the code, so you should always avoid that, or you can copy paste carefully. Okay, so int I, and then we have the my ID and the size, and then we have now, unlike the scatter function, I have send buffer as just an integer, right? Because now we are gathering the data. So send buffer is basically one integer on every process, and then receive buffer is now a pointer because we would like to dynamically allocate this on process 0, because that is where we would like to receive all these send buffers sent by each of the process. Okay, and then we have MPI status, and then we have these first 3 function calls which are of course required. Then if you happen to be process 0, you allocate memory for receive buffer on root. Okay, so when I say root process, or basically on host process, which is designated as 0, okay, then you are allocating receive buffer, and I am not filling in any values in here, just allocated here. And then on different processes, including the process 0, I am filling in the send buffer to be 100 plus my ID square is what I am filling in, some single integer value. Then I am calling this MPI gather function. Again, this is a collective communication that is called by all the processes. Okay, all right, then we have MPI gather, which is basically gathering the data, and then the data that is to be sent is ampersand send buffer. So one single integer of MPI type will be sent by and the buffer that points to is send buffer, and then the receive buffer is of course of the size of 4 times the send buffer, right? It's basically size times the send buffer size, and then but the receive count is only 1 from each process, and then the receive data type is MPI integer, and everything will be received on process 0. Okay, if you want any other process, you have to include that here instead of 0, but because I am allocating only on 0, I would like to receive it only on 0. Okay, and then MPI communicate world is the default communicator. Okay, then because we have now received on process 0, I would print it if my ID happens to be 0, the received values on let's call it host process, that is process 0, are, and then I would print these receive buffer values, and then I would say if my ID equal to 0, then I'm also freeing the receive buffer, right? And then finally I would call the MPI finalize function call. Fine, let us see if this works fine. This is MPI cc program gather dot c. Okay, it compiles fine. MPI run minus np4 and dot slash out. Takes a while. Okay, so received values on host process are 100, 101, 104 and 109. That seems to be fine because that's what I have filled here, right? 100, 1 square, 2 square and 3 square. Okay, that seems to be fine. So my MPI gather function is also working fine. Okay, so we are able to compile it and run it properly. Fine, so that is kind of the first 3 function calls that I would like to, programs that I would like to showcase. And finally, I would like to showcase one inner product or dot product of 2 vectors, both in serial and parallel on MPI. Okay, so this is rather very simple program. So program serial dot product. You're already aware of a inner product program wherein you basically have 2 vectors which are which have some memory allocated here. Okay, for a length of n equals 5, then we are filling in some values in vector 1 and vector 2, and then I would call in a serial dot product which will basically take in the arrays and then calculate its sum and returns it, right? And then that is value is basically printed here. Okay, so this is basically a serial version of a inner product. Now to make it into parallel, essentially what we would like to do is we would like to have instead of partitioning this thing, what I would like to have is, let's say if you are running with 4 processes, you would have vectors of length 20. So what I do is instead of getting in these values and sending them to each process, I would directly work with 5 elements or arrays or vectors of length 5 on every process. Okay, so I don't have to kind of fill them, but then each process will calculate its own local dot product, and all those local dot products will be summed together into one global sum. Okay, so that is how I would have the program. So before that, let me run this program serial dot product, or maybe it's not required. So let's directly go to the program parallel dot product dot c. So what I have is, I have of course the function that is dot product, which takes in 2 arrays, a and b. I just written in floats and integer. Then we have float sum equals 0, and then for loop over all the elements that are being sent to it, and then calculate the sum and return that value. Okay, so basically dot product will return the local dot product that is there. Okay, then let us look at the main program. So main program is essentially you have of course the header files. Then in the main program we send the arguments. Then we have star vector 1, vector 2. I think the tag is not required. I don't like this tag anymore. Let's remove this. Okay, star vector 1 and vector 2 would be the float star pointers. Then n equal to 5, now we'll allocate a vector of length 5 on every process. Then I have a local dot product and a global dot product variables to store them. Then I have the parallel variables are the my ID, which stores the rank, and size, which stores the number of processes and status. Okay, then we have these 3 function calls. Then I allocate memory. This is basically done. Allocate memory on all processes, right? All processes will allocate 5 each, right? So the total will be size times the n will be the total length of the vectors, or the vectors for which we will need to calculate dot product. And then we are filling in some values for the vectors here, I plus 1 plus my ID, so that they are kind of locally getting some values. Then I'm calling this function. This is local dot product, and then you call dot product and vector 1, vector 2, n. So this is also called on each process. So now local dot product only contains the dot product on that particular process. Then we call MPI all reduce. So this is basically is the function we learned. Instead of reduce, we are calling all reduce. That means the local dot product will be from each process will be absorbed, will be collected, and then it will be put into global dot product, and then that will also be communicated to all the processes. So the final result will be available on every process. That's why we use MPI all reduce here. So you are sending in ampersand local date that dot product, and then the final result will be obtained in global dot product, and then we are sending in one variable of MPI float. And then what we would like to do is we do the operator is MPI sum, and then we have MPI communicate word. Okay, and then because it's available on all the process, I would just use forget about these, ignore these comments here for these. Okay, and then we have inner product of v1 and v2 is such and such. Okay, and this is printed by every process. Okay, and then we are freeing the vector 1 and free vector 2 because they are allocated on every process, and finally call the MPI finalize. Okay, so let's see if it compiles and runs. MPI cc program parallel dot product dot c compiles fine. MPI run minus mp4 dot slash v dot out. Okay, so basically it has every process has computed, has received the final dot product. That seems to be around 560, which seems to be correct. Okay, fine. Essentially, that is how you would use the MPI all reduce and the inner product calculations. Fine. Okay, let me quickly also look at the program parallel dot product in Fortran. So in Fortran we have we include MPI f.h in double quotes here, and then we declare n to be 5, and then we allocate dynamic. We would need pointers, so instead Fortran works with allocatable arrays. So we say vector 1 and vector 2, and then you define the counterpart of float is real. So you say real and dimension is 1 dimension, and this is allocatable, so you can allocate it later. And then you define the local dot and global dot, and then you have all these things, and of course I don't need the tag here again. Then you have integer MPI integer status. Then you call the first three functions, that is initialize, communicate size, and communicate rank, and allocate vector 1 to be of size n, vector 2 to be of the size n on all processes. Right, this is basically the same as what we have before. Fill in the values. Now here you note that we are filling in the values. This is 1 to n, right? Earlier we filled in from 0 to n, and then of course plus my ID. So let me also put in my ID here. So this is my ID plus my ID to make it somewhat fill values on all processes to make it somewhat local. But then you realize that it goes from 1 here instead of 0 on the other one. So let me make it -1 here. Okay, that will make it basically same as what we got in the C program. Then you calculate dot product. Fortunately in Fortran you already have a implicit function known as dot product, so I don't have to write a function for this, so that's not available. So it's a an implicit function dot product is already available, so we don't have to write it. Okay, then this basically calculates dot product and then on that local process, and then we would use MPI all reduce like what we have done before, and then local dot. Unlike C, we don't have to give ampersand here because the function calls in Fortran are always passed by reference. So when you say local dot, the address will be sent, so any changes will be reflected here, and then global dot, and then we have 1, and then MPI real, MPI sum, and MPI communicate world. Okay. Okay, then what we have is every process will write the inner product of v1 and v2 is the global dot product, and then we deallocate. Basically this is the counterpart of your free argument, and then you call MPI finalize with MPI error. Okay, let us see if this compiles fine. MPI f90 program parallel dot product dot f90. This is a okay, that's a warning. It says I should not write this comma in between, so we don't write it. Okay, that's gone. Then MPI run -mp4 dot slash a dot out. Okay, it gives the same result as my C code when I change the indices to be matching between them. So that is fine. So that is how you would run it. Now I have a little comments here where instead of the values being printed on using an all reduce, I can even call MPI reduce, which of course has this additional argument 0, right? That is the only difference between these two. So let me call MPI reduce instead of MPI all reduce and see if it works fine, and then I would only print it if it is let's say only process 0, because now the data is collected only on 0, and then I deallocate vector 1 and vector 2. Okay, let me call this, I compile, run again, hopefully it will run. Segmentation fault, invalid memory reference. What is the problem with this? Okay, so I got a segmentation fault. Okay, let me try to fix that. What is the problem? MPI reduce local dot. Okay, my ID equal to 0. So vector 1, vector 2 is allocated on all processes, right? And then I'm freeing them. And then if it happens to be process 0, then only I am sending it, right? Okay, let me see if I can try to debug this. Minus G, minus wall. Okay, unused is okay. Then MPI run minus MP4 dot slash a.out. Hopefully it will print some debug messages so that I can. Okay, it does print. It says 26, line number 26. There is some issue. Okay, basically from there it's calling. Oh, some issue with this. Okay, local dot global dot is my call to MPI reduce not correct. I should have. Oh, maybe I should have MPI error at the end, is it? Or import run. Maybe I should have MPI error at the end. That's the reason why it is giving a segmentation fault, maybe. Okay, then let me add that. But that should have been given as a that should be given as a warning, isn't it, instead of a segmentation fault. Okay, anyway, I will try to fix that later. So I have destination process, I have input data, output data, count, then I have the data type, that is MPI real, then I have operator, that is MPI sum 0, and then MPI communicate word. I think that seems to be fine. I don't know why it's giving an error here. Right. Okay, I would not worry about that at the moment. We will fix that later. Okay, fine. So that's all I wanted to kind of showcase in terms of programs. Then let us move on to the MPI altogether, right? So before that, I would kind of introduce you kind of some motivation. Let us kind of, before we move on to altogether, let us consider a matrix vector multiplication. Okay, so basically we have a multiplication, let's say, using or in MPI. Okay, that means we have, let's say, a matrix, okay, which is A11, A12 all the way to A1n. We have A21, A22 all the way to A2n, and then we have AN1, ANN, right? And then we have x1, x2 all the way to xn. And of course on the right hand side we have b1, b2 all the way to bn. Okay, so that's what we have. Now what is a logical way of let's say this matrix is n by n and it is also dense. Okay, so a logical way to partition this in MPI seems to be in a blockwise manner, or a blockwise decomposition seems to be a good way to deal with this matrix vector multiplication. So a block decomposition, and that too in a along rows, seems to be a good way to do this, because then we could assign few blocks to process 0, and then few blocks to process 1, and then few more blocks to process 2, and so on. And each process, because the way the matrix vector multiplication works is that you would need all these values to be multiplied with this, and then it has to be stored on a particular in a particular variable, right? So essentially this has to be, that means the blockwise partitioning should be such that should be such that this value okay, one more. Okay, so then this value should also be stored on the same process as this one, and then similarly these values should also be stored on the same process as the previous one, and then and these ones, and so on, right? So essentially we would like to keep these values and these values on the same process, and then these values and these values in the same process, and so on, such that they can be easily multiplied with this unknown vector, and then or the known vector, and find the basically the right hand side. Okay, now what about this vector x? Now should x be also partitioned like what we have, or should it be available on every process, the entire array? Actually the entire x array needs to be made available on every process, right? Because it is kind of required to multiply for this entire row. Okay, so if you use a block partitioning for the x, which is probably something like this, then it is probably not a good idea, because you would need these data as well. But what happens many a times is that because of the way the algorithms work, even this vector would also be kind of only available in a partitioned way. Okay, so x tilde will usually be available in a partitioned way, just like vector b. Okay, so if that is the case, then but we know that these part values available on every process are not sufficient to compute the matrix vector multiplication. So as a result, we would need the entire x data on all the process, right? So that means we would need, for the program to work, we would need all x tilde on all processes. Okay, then that means we would basically need a gather function, and then that should be an all gather function, right? So what we would do is, I mean, what we could have done is basically we could have done a MPI gather followed by a function call to MPI scatter, but we know that that basically involves two tree structure calls, right? Because MPI gather would have one tree structure like call, and then scatter will have another tree structure call, and then instead in some cases probably it is easy or better to work with a butterfly communication, you know, and such a thing is usually provided by an optimized way of communication will be provided by MPI, and the function call is MPI all gather. Okay, so which will take care of, which will avoid kind of we calling two different functions. Instead we could just call just one function. Okay, so this simple function, let us see what is the function prototype here. So this is int MPI all gather. Okay, and then what we have is of course similar to gather we would have a send buffer, so void star send buffer pointer, and then we would basically have a count and data type. So this will be integer send count, and then the data type would be MPI data type. So this is basically the send type. Then we have void star receive buffer pointer. So essentially whatever we have, it will kind of repeat for the receive section. So we have receive count, and then we have of course the receive type. So that is again MPI data type receive type. Then we have so these three arguments which are same as before, and then we would have of course the communicator. So that is basically MPI communicator, right? Oh, maybe if I go back to the program, I think it's fine. Okay, MPI communicator. So when your program doesn't work, you always go back and look at it until it gets, I think it until it fixed, right? Until it's fixed. So I'll try to fix it and then send you an update. Okay, so now, all right. So basically this function now what it does is it will basically assemble the contents of each process's send buffer, right? It's kind of going to assemble the contents of each process send buffer into the receive buffer, right? And then it does this on all the processes, right? It will basically do it on all the processes, and then the send count will usually be the same as the receive count, right? Right, it will be same because this is the amount of data that is being sent and received, and then when essentially the send type and receive type and the send count and receive are the same, right? Only thing is the send receive buffer would be much larger, or essentially the size of the send buffer times the number of process, and that needs to be allocated accordingly such that there is no segmentation fault or something just like what I had now. Okay. Alright, so that is about the MPI all gather function. Now we so far so fine. So let us move on to the final topic that we would like to discuss in today, that is the MPI, derived data types in MPI. So MPI derived data types. Okay, now derived data types are a great way to send a different data type elements in one go across process. Okay, so essentially we all know that, or it is kind of known that in all distributed memory systems, the cost of communication between the process, I mean, when I say cost of communication, it's basically the the time it takes to send a communication is much larger than a local computation. Okay. So what we mean by an example is basically, let's say if you would like to send a you would like to send a double value from process A to process B. This will basically take much longer time. This will take much longer time than let's say adding or multiplying, adding the two doubles together on a local machine or a process. Okay, so that means the communication is kind of expensive, it takes longer, so we should try to optimize the amount of communication that we send. So that means this kind of also draws us to how we partition our boundaries, how we partition our boundaries or our domain also matters, right? Because we don't want to partition it in such a way that the communication communication is a lot more. Rather, we would like to partition it in such a way that the amount of data that needs to be exchanged is as minimum as possible. So amount of data exchange needs to be minimized, and then that is how we would like to partition our domain, or whatever partition our program that we are trying to do. Okay, because a send receive is always much more expensive than doing a local floating point arithmetic. Okay, so and then and further, so that is one thing. The other thing is, further if you would like to send a, let's say, a fixed amount of data. Okay, that means you want to send few integers. It may not be in a continuous way. Let's say you would like to send A, B, C, some few values. Okay, let's say some 10 double values between, let's say, two processes. So you have process 0 and then you have process 1. And if you like to send 10 values, so sending 10 values in 10 separate messages is much more expensive than sending all 10 messages in all 10 values as a single message. Okay, so we should always try to send as much data as possible in one go than sending separate function calls. For example, let's say I would write two small programs here. The first program is, let's say we have a double array, x is 1000. Okay, and we would like to send this, and then we have process 0 and process 1. And on process 0, I basically have, if let's say my id equals 0, then what I do is I send for I equals 0, I less than 1000, I plus plus. I would write a function that is basically MPI send. I would send ampersand x of I, okay, in each function call, and then I have one value I will send, MPI double, and then I would send it to process 1, and then 0 is the tag, and then I have the communicator, okay. And if process is not 0, else what I would do is I would receive those 1000 messages, right, in a function call MPI receive, and receive into x of I 1 MPI double, receive from 0, and 0 is the tag I would send, and then communicator, okay. So this program is one which will basically send 1000 messages, right. And then the second program, again we have, let's say, double x of 1000, and then if my ID equals 0, and I have for, I don't need for now because I would like to send all of them in one go, so I would just have MPI send, and I would send the base address, that is basically %x, right. And then this is your 1001, then you have MPI double, right, send it to 1 0, and then communicate, right. And then if you have if you're on process 1, then you basically receive MPI receive %x 1000 elements. What is this one here? There is no one here, just 1000, right. MPI double, and then receive from process 0, and then 0 is the tag, and then you have the MPI communicate world is the communicator. Okay, so if you run these two programs, what you would notice is that in the first one there are 1000 sends and receives. In the second program there is only one send receive, right. So you will notice that the first program is much slower than the second program, and how much this is slower, that kind of depends on the interconnect and things like that. And the slowness or the time it takes could be, the first program could probably be taking maybe 50 times or more time than what the second program takes to finish, okay. So we always expect that the as many send receive function calls we have, the program will be, you know, so much slower, okay. So so we should always try to reduce the total number of messages you know, we send, so that we can improve. So always try to reduce the total number of messages, so that we can improve the performance of our program. Okay, fine. So well, essentially message passing interface provides 3 ways of improving the performance, or improving the performance by the way of reducing the number of total messages. And those are, the first one is the count argument, right, which I have just used and demonstrated. The first one is the count argument, using which we can send contiguous data across process. Now sometimes you may not even have contiguous data. You would like to send, let's say, different data or different data type, and they are not even contiguous. Then you have another thing that is provided by MPI, that is the MPI derived data types. So you could kind of what do you say, declare or define a derived data type, and then essentially MPI would send a certain number of those derived data types in one go. Okay, this could be very much useful. We will come to that. And then the third way of you know, improving the performance that MPI provides, third lever, is basically your functions MPI pack and MPI unpack, which will also kind of pack all the data and send it, and then it will unpack on the process on the receiving side, and then it will going to assign those data values. Okay, so we are not going to we have basically looked at the how to use the count argument. We will look at the derived data type, but we will not look at pack and unpack. Rather, you can kind of look it up for yourself and then understand that part. That should be straightforward. So we will concentrate on the derived data types. Okay, so how do we build a MPI data type? So how do we build an MPI derived data type and use it is the question. Okay, so building an MPI derived data type. Alright, so basically what MPI does is, you in MPI, if you have a derived data type, it's basically a collection of data items in the memory. Basically this is basically a collection of data items in the memory, that basically together with the data type and the addresses. Okay, so basically our addresses are their relative locations in the memory. That means we would like to specify what is the data type that basically tells MPI that how many bytes of memory needs to be read from a particular address, and then we need to specify the relative locations of all those addresses of all the variables, such that this collection of data items can be thought of as a particular derived data type. Okay, this is kind of similar to structures that you have in C. Okay, so essentially the complete idea is that instead of sending, let's say, different values using multiple messages, if you can put all of these things together. So basically, if you have a particular function which is, let's say, is achieved using MPI derived data type, wherein certain memory locations and the data can be somehow specified with a pattern, then MPI would do basically collect all of these things and then send as a single message. And then once on the receiving process, once the data is received, this single message, whatever is sent, will be put in the same places as required on the receiving process. Okay, so that is the idea, such that the overhead of send receive, being called multiple times will be reduced. Okay, so that is the complete idea. So let's say if you kind of consider the trapezoidal rule function, right? The trapezoidal rule program that we have written, we have to, if you have read the A, B, and N values from the user, then we have to use 3 separate MPI send for A, another send for B, and another send for N, and so on, right? So we have to use 3 such function calls, or we could have replaced these MPI send receive with 3 MPI broadcast calls, right? Because we have used different, these are basically 2 double values, and then this is 1 integer value. So instead, if we have a particular data type, we could have actually packed all of these into one particular data type, and then MPI would have sent as a single message instead of 3 messages. Okay, so then we would not have required these 3 function calls. Instead, we would have just used 1 function call. Okay, so for which we have to basically build a data type, a derived data type that consists of 2 doubles and 1 integer. Okay, so need to come up with a derived data type that contains 2 doubles and 1 integer, right? Then this could be achieved. Okay, now how do we achieve this, and what are the specific details of implementing MPI derived data types, and what are the required function calls? That we are going to see in the next lecture. Okay, I'm going to stop here in the interest of time. Okay, thank you. Talk to you in the next lecture.